Sample question 6.1 asks us to explain briefly why A, increasing the concentration of the reactants usually increases the rate of a chemical reaction. Well, that is because more reactants are present, and therefore there will be more collisions. If there are more collisions, those collisions are more likely to collide with the proper orientation as well as energy for a reaction to occur. Part B asks us if a reaction does not occur every time the reaction species collide, why that is. And that is because sometimes they either don't have enough energy or they're not in the correct orientation, so they have electron clouds bouncing in and repelling one another, and the reaction doesn't occur. It also asks us to explain why increasing the temperature increases the rate of a reaction. That is due to increasing the number of collisions as we increase the temperature. Temperature is a measure of the average kinetic energy of the particles involved. So if we're increasing how much they're moving around, more likely they're going to be increasing the amount of times they bump into one another. And hopefully, again, with that right amount of energy and with the right amount of, with the right orientation for the reaction to occur. Sample question 6.2 asks us to explain what the rate determining step of a mechanism is. And all that is the slowest step. So if it's a multi-step process, if multiple things have to occur within the reaction, whichever one takes the longest is called the rate determining step. It tells us the fastest our reaction could possibly go based upon our slowest part. And then finally, sample question 6.3 says the activation energy for the reaction below is 112 kilojoules per mole, and the delta H is positive 57 kilojoules per mole. The reaction is 2NO2 is in equilibrium with 2NO plus O2. First of all, it asks us to draw an energy level diagram illustrating the energy changes for this reaction. So, we first notice that it is telling us that we are changing the energy and we've got, let's put this, we're not doing it to scale, but let's put our 112 kilojoules per mole up here, and we know that takes some energy to get there. We also know that the delta H is a positive 57 kilojoules per mole. That means that I have an endothermic reaction. More energy has to go into the reaction than is actually released when the bonds are formed. So that means that my reactants are more stable than my products, as this is my time change. This I know, this little bump up here is whatever my activation energy is. And sometimes we just label that with an EA. And then it says, on the same diagram, using dotted lines, show the effect of a platinum catalyst and label it clearly. So if I add a platinum catalyst, my activation energy would be lowered. So here's my addition of platinum. Lowers the activation energy, so it's easier for the reaction to occur. In C, is the reaction exo or endo? Sorry, I explained that already. It's endothermic because I have a positive delta H. And when it occurs, will the reaction become hotter or colder? It will actually feel colder to the touch because energy is going into the system for the reaction to occur. And if the temperature was increased, how would that affect the rate of the reaction? So, with that one, it says that if we are making it colder, we're actually going to make the reactants collide more frequently. And so that should increase the rate of the reaction. And then what other factors could change to increase the rate of the reaction? You may want to think about increasing the pressure. If you increase the pressure or decrease the volume, both of those things are very closely related, we should increase the amount of collisions that you have.